Let us show that the given function dxy, which is equal to the absolute value of x minus y, is a metric on R, or the set of real numbers. In order for us to show that the given function is a metric on R, it should satisfy four conditions for metric. Now, we have here, let x for generalization be equal to a real number, a set of real numbers, and let's define the function d as the mapping of x and x into R by the function d of x and y is equal again to the absolute value of a difference. Now, the first condition that should be met, we commonly denote this as M1, is the idea that the given function is greater than or equal to 0 for all values of x and y element of our set x, or in this case, set of real numbers. If we could establish that, then we have satisfied the first condition. Of course, take note that our given definition for x and y for this item is actually the absolute value of a difference. And this is always greater than 0 because of the absolute value notation. Whatever be the value of x and y, as long as they're element of our real numbers, when they are subjected to difference and the absolute value notation, they're always greater than or equal to 0. This would mean that M1 is satisfied already. Let's proceed to M2. M2 states that if the distance of xy is equal to 0, this only means that x is equal to y for all x and y element of the set x, or the set of real numbers. So we need to establish this so that we could really satisfy M2. Let's take note that since this is bijective, we need to show both directions. So let's start first with this, and let's say that the distance of x and y is really equal to 0. Take note that per definition, the distance of xy is, for this given item, is the absolute value of a difference, which is equal to 0. Now take note that this is under absolute value notation. This could only be equal to 0 if the quantity inside the absolute value, sorry for that, is equal to 0. Hence, x, by moving y on the other side, is equal to 0, and we have satisfied this direction here. Now we need to show the other way around. Okay? And we say that x is equal to y, and then we need to show that the distance between them is 0. Of course, if they are equal, and our definition for our distance of x and y is equal to the absolute value of the difference, and let's say we substitute x for our y, or you could also use y to x vice versa, because we have assumed that they are equal. So you can have x and x, you have your x minus x, and we know that that's absolute value of 0, which is equal to 0. So we have established the other way around by assuming that they are equal, and we have shown that the distance, which is this, is equal to 0. Hence, M2 is also satisfied. Let's proceed to M3. So we have here M3. The condition for M3 states that the distance from x to y is just equal to the distance of y to x for all x and y element of our set of real numbers here. So we need to show that. Take note that per definition in this item, the distance between x and y is represented by the absolute value of a difference. Now, what if our goal is to reach this item here? So please bear with me. Let's try to rearrange the terms. Of course, it's still negative y and it's positive x. Let's factor negative 1. So you will have y. What happens to addition will become minus, just like that. And there is a property for absolute value. Once we have a scalar quantity here, this is just equal to the absolute value of the scalar quantity and the times the absolute value of the expression. Of course, we know that the absolute value of 1 is just 1 times the absolute value of y minus x, which gives us the same expression y minus x. And what does this represent? This, per definition earlier, we have x and y, so you have x and y here. Once they are interchanged, this is also equal to the distance of y and x. This is M3, and it is satisfied. So we are down to our last condition for our for this function d be considered as a metric on the given set. So let's have M4. Hopefully my spaces here would be enough. So for M4, this is on triangle inequality. By the way, M3 is on symmetry, that they are just the same. M4 is on triangle inequality. Let's say there is a certain another variable z. We have to establish that this is less than or equal the sum of the distance of x and y plus the distance of y and z for all x, y, and z element of our real numbers, or in this case set x. So how do we show this idea? Now take note that we can always manipulate both sides as long as we could reach that the this value is less than or equal to the sum. Okay, so let's take for this this time. So you have x, sorry, we are still on d, so that's x and z. Per definition, this is the absolute value of x minus z. Take note that our goal should reach or an expression with y. So let's try to add certain one inside the absolute value notation in terms of y plus y. This is just equal to 1, so you're not changing the value inside. We're just trying to introduce y because our expression for M4 needs a variable y. So again, we are not changing the value of this because this is just equal to 1. With this, there is a property for absolute value which tells us that if we could establish a certain sum of two expressions inside an absolute value notation, this is overall less than or equal to the sum of each absolute value notation. In short, this is less than or equal x minus y plus y minus z. Okay, so this is one of the property for absolute value notation. Again, if we could establish sum of two expressions inside absolute value notation, that is less than or equal to the sum of the absolute value notations of those expressions. And what is this? And what is this? Going back here, the absolute value of x minus y plus the absolute value of y minus z. This, per definition, could stand to the distance of x and y plus the distance of y and z. So this is equal to this expression. This is equal to this expression, which is greater than or equal to our given expression here. Hence, we can establish that the distance of xz is less than or equal, that's less than, let me rewrite it, less than or equal the distance of xy and the distance, sorry, let me rewrite it here. Okay, so again, this establishes that the distance of x and z is less than or equal to the sum of distance of x and y and z. M4 is satisfied. Okay, so with M4, M3, M2, and M1 being satisfied, we can now say that therefore D defined with this expression is a metric on our set of real numbers. And further, if you would like to, you can say that this expression is what we call as a metric space. We can only establish the idea of metric space once we have established that the certain function d is a metric on the given set. So this is for this first item. We'll have more examples on our channel. Thank you very much for watching.